All right, welcome back. We're going to begin today with an introduction to waves, a very important concept in describing the world around us. Waves are everywhere. Obviously, we see waves in the ocean or on the lake, but the concept of waves, as we'll see, can be applied to so many other things. It can even be applied to things that don't actually look like waves, but still, in a certain way, behave like waves. And so that's why they're critically important to understand. Even the electrons in an atom. You may have heard, if you know anything about the quantum mechanical model of the atom, we talk about electrons as waves. And so understanding waves is critical to all areas of physics. So let's begin with something very simple. Now let's imagine a little spring with a weight that's hanging on it, right? And it's just sitting there doing nothing. What would happen to the weight if I grabbed it and I pulled it down? Well, that would stretch the spring and create a force in the spring. And then when I let go, the object would spring back up past where it went. It would spring up until the spring sort of squished up or compressed, and then it would bounce back up and down and back up and down, and it would probably do that for quite some time. Eventually, it would sort of slow down because of the energy losses due to air resistance and friction and the heating up of the spring and all kinds of stuff like that. But if we were to imagine an ideal spring that never got tired, that never wore out, never had friction, never had heat, this possibly could go on for a very long time, if not forever, bouncing up and down, up and down, up and down. And what's important to notice is that there's a center point where it was hanging freely, and it bounces up past the center, and then on the way back down, it also goes down past the center. And it would be the same up and down on both sides, same distance. And so this bouncing up and down spring would just keep on going. And what we call this in physics, we call this simple harmonic motion. The motion of a spring that's just bouncing up and down because somebody's pulled it or displaced it in some way. And it would bounce up and down, up and down, up and down. But if we were to make a graph of this motion, let's do a little graph beside it. And on the graph, we'll take time passing on the x-axis, and we'll graph the position of the mass on the y-axis. Well, let's look at what happens up here. When the mass has moved up, it would be reaching a position that would be higher than where we started. So I'm going to put that position right here. Let's say that's where that graph would be. But then later, it bounces back down to a position lower than where it started, and it's the same distance away, so I'll put that distance down here. So if we start with it in the middle, and then I grab it and I pull it down, so I'm holding it at the bottom, right about here. And that's when I let go. That's when the simple harmonic motion would begin. We would have to start our graph down here at the lowest point. And when I let go, as time moves on, the mass is going to move upward. And it's going to move up as I go. So the graph would show this, up, 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 until I got to the middle. But then I would go past the middle, up, 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 and then I would get to the top. And then once I got to the top, I would spring back down again, down, 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 and all the way down. And this is what the picture would look like if we kept going. I'm kind of running out of space there. But what we see is an up and down motion sort of stretched out because of the time passing on the axis. And when you look at the blue line, you can't help but think, boy, that looks like a wave, doesn't it? It looks like what happens on the beach when we see water. And so this simple harmonic motion is actually a wave in disguise. Mathematically speaking, it works like a wave. It repeats itself from one position to the next, bouncing back and forth over time. You'll also notice that this graph looks a lot like a cosine graph. right? In fact, the graph of it's an inverted cosine, and sometimes they'll look like sine graphs. And in fact, when we get into the more complicated mathematics of waves, we use the sine and the cosine functions, which are sometimes called wave functions, to describe how waves work. And so when you see this picture, you can see why we're going to use those down the road. But for today, we're not going to get into the math. We're not going to worry about that. Just keep that in your back pocket for later. We just want to get an idea of what's going on here. Now, we can actually see this in action. We don't need a mass bobbing on a spring. Let's take a simple piece of string. I'll stretch it out here like this in black. There it is. Now what would happen if I grabbed the end of the string right here and I moved it upwards very quickly? Well, the whole string would sort of bend up. But because a string is made of molecules, and all the molecules inside the string, are attached to each other by what we call van der Waals forces, right? There are little forces. You can kind of think of them visually like little tiny elastics that are holding all of the molecules of the string together. Well, when you pull up one end of the string, you pull on the very first few molecules of string. Those molecules then pull on the next ones and the next ones and the next ones. And then what we would get is a sort of a bubble happening. If I lifted this up fast and then brought it back down again, then the string would produce a bubble. And that bubble, as it pulled, it would pull up, it would keep pulling on all of the molecules. They would each get pulled up. And then they'd get pulled back down again. And this bubble would travel along the string. It would slide sort of sideways along the string. Okay, give it a try. Grab a string, give it a quick snap up and down, and you'll see this bump that travels down the entire length of the string. Now what's interesting is, I didn't push it down the string. All I did was lift the string up and then back down again. But the bump, or the bubble, has traveled sideways all the way through the string. And that's an important part of waves. Waves happen as sort of like an interesting phenomenon, but the direction that they travel is not always the same direction that you wiggle the string in, which is kind of weird. If I were to take this same string and I were to snap it very quickly up and then down, all the way down past where I started, and then back up again, sort of three motions, I would produce a wiggle that looked like this. And that wiggle would work its way down the entire string, and I would see that wiggle. If I did it once, I'd get one wiggle, but if I kept doing it over and over, like simple harmonic motion, just like the mass bouncing on the spring, then I would keep producing these bumps, and they would all be sort of traveling down the spring, or the string this way. And this is exactly the kind of wave that we want to talk about first. What's interesting about this kind of wave is that the direction that you are wiggling is different than the direction that the wave actually travels in. Okay, so let's get some terminology into our heads now that we have this picture. In order for a wave to occur, so let's write down, for a wave to occur, there has to be something that is vibrating. The word vibrating is sometimes used, which means moving back and forth. Or another word that we use, and in fact, when I was studying physics, my teachers and professors tended to use this word a little more often. Another word that means sort of the same thing is oscillating. You've heard of an oscillating fan? Maybe an oscillating fan turns one way then the other, and one way then the other. It goes back and forth, so it oscillates. So this is probably a better word to think about. But when we talk about sound waves, we often use the word vibrating as well. They mean the same thing. Something that's moving back and forth. We could say that the mass on the spring that I gave you in the first example, right here, is vibrating up and down, up and down, up and down, or oscillating, changing positions. Now, the something that is doing the vibrating, whatever that is, has a special name. It's called the medium of the wave. And it's important for us, a little extra I in there, and you, the medium of the wave. It's important for us to distinguish that the wave itself is not the thing that's vibrating, but it's the phenomenon that appears when something vibrates. Okay? I'm going to give you another example to show you the difference about those two things. Let's say you're at a sporting event and you're all sitting in the stands, hundreds of thousands of people. Well, one person stands up and raises their hands, woohoo, but then they sit down again. And when they sit down, the other person stands up and raises their hands. And you know the idea, we do what's called the wave. Now what's important to realize is all the people are doing is standing up and sitting down. But a weird phenomenon happens. For the person who's watching from across the stadium, there's a ripple effect. As each hand goes up and the hands behind go down, right? Then the next one, the hands go up and the hands behind go down. Each time that happens, you can see the hands up are like the bump of the wave, and they keep moving this way. So the wave, the bumps of the wave, are moving this way. When we do the wave at a sporting arena, it's usually just one bump that moves all the way along. But if you kept doing it, if you started again and again and again, you'd get one bump after another. But wherever the hands are up is where the bump of the wave is, and it travels sideways. So the people are not moving sideways. People are not running across the stadium. They are simply standing up and down. And so we're going to give two different names to these motions. The up and down motion is called the direction of the vibration or the oscillation. Okay? A vibration or oscillation. But the red one over here is the direction in which the bump of the wave seems to move, and that is called the direction of propagation. A wave propagates, which is a big word that simply means propagates, which means moves along. Direction of propagation. Sorry, I got my words mixed up. Propagation. And what's important to realize is when we do this wave with the sporting arena, or when we do the wave with the string, the direction of propagation and the direction of oscillation are not the same. Let's write this down. The direction of oscillation is actually perpendicular, right? It's perpendicular to the direction of propagation. The direction of propagation. Okay? And so just pictorially speaking, we can draw this way and this way. Right? This is the oscillation direction and this is the propagation direction, perpendicular to each other. When that happens, we have a very specific kind of wave, and that kind of wave is called a transverse wave. So that's another word for your vocabulary. Transverse wave is a wave where the direction of oscillation is perpendicular to the direction of propagation. And you can think of examples of that as the wave you do at the sporting event, or the wave on a string, or even waves in the water to some degree are pretty much transverse waves that you see on the seashore. Not so much on the shore where the waves are breaking, but out deeper where the waves are rolling. Think about rolling waves. Breaking waves are a little bit different, a little more complex. So think of rolling waves when you think of transverse waves. All right. Now there's another way to make a wave. So let's leave that for a second. And let's try something new. Look at a different way of making a wave. What would happen? I want you to imagine if you had some water. Now, water is like a fluid, but I'm going to draw a whole bunch of water molecules here like this. Water molecules sort of all together in the water. What would happen if I pushed against the water? Like I took my hand and I pushed hard against the water. Well, I would cause some of the water molecules at the start to get all bunched up. They'd be squished together, and then the rest over here would not be. Right? But this squished up bunch of molecules, remember molecules have forces that attract them together, but if they get too close together, they also repel each other because they're each surrounded by a cloud of negative electrons, and negatives repel negatives. So the clouds of electrons between molecules and atoms and ions and things tend to push away from each other if they get too close. So if I squeeze all these guys together, then what will happen is these little guys right here will begin to squeeze, they'll want to get away from the others who are squishing them. And they'll push against the others. And then what will happen then is as they move away from each other, the squeezy part gets moved over here. And then those people, or those molecules, will squeeze against the other ones, and the squeezy part will move a little further. And so what we have here is a squished up bunch of molecules that tends to ripple through the water. If I were to pull back on the water this way, it would be the opposite effect. I would create an open space where there are less molecules. And then those little molecules would pull, as they get too far away, kind of like little elastics between the molecules, and they would stretch out the next piece and the next piece and the next piece, and you would get the same idea. So what would happen if I had simple harmonic motion where I simply pushed forward and then pushed back and kept doing that over and over and over? Every time I pushed forward, I'd make a clump. And every time I push back, I'd make a stretched out area, and then there would be another clump and another stretched out area, and I would get this repeating pattern of clumpy spots and stretched out spots in the water. Now, instead of drawing dots, we sometimes draw this like this. We draw it as little lines to show molecules close together, and then molecules far apart, and then molecules together, far apart, close together, and so on. What we're actually doing, the real word is compression. We are compressing the molecules. And so we call this spot where the molecules are squished a compression area. And then when the molecules are spread out, we use another word that kind of represents the opposite of compression. It's not a very common word. It's called a rarefaction. And that is a word that describes the open or less compressed spot where you pushed the other way. But you can see what happens. Just like with the transverse wave, we got repeating bumps and dips and bumps and dips. Now we're getting compression, rarefaction, compression, rarefaction, compression, rarefaction, all sort of interspace between each other. We're getting a repeating pattern. This kind of wave is different because the blobs of compression are moving through the water this way. But look at the way we are vibrating or oscillating. We're moving our hand or some object back and forth in the water, this way and back and forth and back and forth. And we're creating compressions that are also traveling in the same sort of line. So the difference for this kind of wave is that the direction of oscillation which is this direction here, the way you're wiggling the water, is, I'm going to have to go underneath here, is parallel. It's not perpendicular, it's parallel to the direction of the propagation of the wave, the direction the wave goes, propagation. They're both in the same direction. So to draw it visually, you have this way is the way you're vibrating, that's the oscillation direction, and this is the way that the wave propagates. You see how they're lined up. This kind of wave is given a different name. It's called a longitudinal wave. Or sometimes we call it a compression wave, because as we saw, it's a wave that forms from compressing. So you'll sometimes see this called a compression wave, but it's a longitudinal wave. So you'll need to get your head around these two different types of waves and their main difference between them. Now what we're going to do to help you with that is draw some pictures to help give you a visual. Visuals are always good. So let's draw a picture of a transverse wave first. Here is a transverse wave. So it basically has there's an axis, like a graph axis, and we'll superimpose on that a nice transverse wave. There it is. Okay? And what we're going to do is we're going to label some parts, get to know this wave. So first of all, remember that to make this wave, we vibrated something that was bouncing back and forth from 2 points. Right? It was vibrating back and forth, up and down like this over time, creating this wave-like picture, like a string. We were moving the string up and down. Well, what you first notice is that there are spots where we reach the highest possible point of the spring, which in mathematics we would call a maximum. But in physics we sometimes refer to this as the crest of the wave. The crest, maximum, or crest. And then there are other places where the string is in the position at the lowest possible spot, which of course we call a minimum. Or sometimes we call it a trough. It's the opposite of a crest, a trough. So we have these names for the uppy and downy regions of the graph, or the wave. The other thing we like to look at is the distance that you have moved the string. So remember, we started here, and we lifted the string a certain amount, so I'm going to put a little a there, because the word we use for the amount that the string has been displaced or moved out of the way, off-center, is called the amplitude of the wave. And of course, the amplitude is the same on both sides, except one is one direction and one is the other. So this one would technically be a downward A or a negative A. But normally when we talk about amplitude, we just think of the absolute value of it. We think of the magnitude only, because we understand that waves have uppy parts and downy parts. But we recognize that those two things are the same. So I better write that down here. A stands for amplitude. And it is basically the amount of displacement all right? So you could think, for instance, a very low amplitude type example, low amplitude wave would look like this. The wave would have very, very shallow bumps. You're not really moving much or displacing much. But a high amplitude wave would have very pronounced movement, right? Differences like this. So it's basically how much you're going to wiggle, how far you're going to wiggle. Okay? One more thing to look at on our wave. If you look at the red line, I want you to focus your eyes from this point right here to this point right here. And you'll see that the wave goes up and then down and then back up. And then, once you get to here, you're actually starting the exact same thing again. It's the same as being over here. And you'll notice that there's a piece of this wave, everything follows along exactly until you get to this point. And then you would start over again. There are repeating sections of the wave. And the length of a repeating section of the wave is called the wavelength. Okay? And the wavelength is used, L is already used for so many things, so we use a Greek L, which is a lambda, which looks like this, and it's spelt like a little, Mary had a little lambda, with a B in it, because it's Greek. It stands for the wavelength, and it's the length, it's actually measured in meters, it's a length, but it's a special length. It's the length of the repeating unit. Or the repeating part of the wave. Okay, just length of the repeating part of the wave. Another way of saying that is it's the distance between corresponding points on the wave. Corresponding points on the wave. By corresponding points, we mean places that are in the same section or the same part of the repeating unit. For instance, the two green lines that I've drawn here are the two green points here and here. They are corresponding because they're both on the upward swing of the wave at the start, right? But you could imagine taking a ruler and putting it on these 2 points and sliding it all along the wave. You could also pick this spot right here, and that's sort of on the downward side, about halfway towards the axis. So the corresponding place would be over here. This is the same sort of spot. But you'll notice that the distance between here and the distance between here is the same, assuming my picture was drawn super accurately. One of the easiest places to see corresponding points is when you look at a crest to a crest. So the crest to crest difference is also 2 corresponding points, and that's a good place to sort of visually think of the wavelength. Or, likewise, it's easy to see trough to trough. But technically, you could pick any 2 corresponding points on the wave and determine what the wavelength is, right? You can also do it by focusing on this repeating section of the wave and how it repeats. Either way, that's the wavelength. Let me show you 2 examples of a very long wavelength and a very short wavelength to give you an idea. So here's a long lambda, or a large lambda, where the wave goes up and back down, up and down. You can see there's the repeating. I only had room to draw one section of the wave. But a short lambda would be a wave that goes up and down and up and down, and many, many repeating units will fit here in the same distance, you see? So here is the wavelength. That's about 40 centimeters, or on my board, on your screen, it's about 10 centimeters. And then here is the wavelength of the little guy. That's about maybe 1 centimeter or 2 centimeters on your screen. So there's a difference in wavelength. Where it gets a little tricky is when you have amplitude and wavelength kind of changing at the same time. So let me give you a couple of examples of that for visuals. Here is, I'm going to draw a certain wavelength, and I'm not going to change the wavelength, but I'm going to change the amplitude. So here's a wave, right, with a big amplitude, and here is a wave with the same wavelength, but a small amplitude. So if I draw the repeating units, here's where they are. There's a bump and a trough, and then right there. You can see the bump right here and the bump right there, the trough right there and the trough right there. So the wavelength has not changed, but the amplitude has. However, now I'll draw 2 lines that have exactly the same amplitude but different wavelengths. So here is one, and here is the other. And I'm going to draw it side by side so you can see it. There we go. So if you look at the length of the repeating units, here is 1. That's all it is. It's that much. But my repeating unit here is much bigger, so it's a longer wavelength. However, if you look at how far I'm going this way, how far I'm stretching up and down, or how far I'm displacing the string, you'll see that it's the same all the way across. See that? Okay, so you have to get your head around what those two things look like. Excellent. Now, what about our friend, the compression wave? The longitudinal type of wave. Well, let's draw a picture. We kind of already have a picture, but what I'll do is give you another one. What we have here is a series of compressions and then rarefactions. So you might want to write a longitudinal wave here so we can longitudinal. Let's spell everything right so we don't get the English teachers upset. Longitudinal wave. And maybe I'll just move it down a bit so we're not too tight there. All right. So we have a compression and a rarefaction, compression, rarefaction, compression, rarefaction, and so on. So I'm going to put little, the compressions and the rarefactions, I'm going to color code it. Up here we had amplitude of the wave, and we had crests and troughs. Okay, so in blue we had the crests and troughs, and the amplitude was purple, and the wavelength was green. So let's try and do the same thing here. Let's see if we can identify where the crests, there aren't really crests and troughs, but there are compressions and rarefactions, right? Compressions and rarefactions. The compression is the place where it's most compressed. That is sort of analogous to the crest of the transverse wave. And the rarefaction is like the trough. They're kind of the same idea. So we don't really have crests and troughs, but we have, I'll just write compression and rarefactions. You can look at the words up above if you've forgotten what they are. Okay, what about the amplitude? Well, the amplitude is a little bit difficult to see on here. On this kind of a wave, the amplitude refers to the degree of compression. The degree of compression. How much compression is there? So let's draw a couple pictures to figure that out. What we would see here for a low amplitude wave would have a compression and a rarefaction that are very hard to tell apart. In other words, the amount I'm compressing the compressions is not much. You can barely make out the compression here and here and here. But a high amplitude compression wave, a high amplitude compression wave would have a very noticeable compression. Let's draw that one. It would have a very strong compression and a very noticeable rarefaction, and a very strong compression, a noticeable rarefaction. So the amount of compression is how you determine the amplitude of such a wave. The wavelength, again, just like before, it was two corresponding points on the wave. It's the same thing here, but the corresponding points are harder to see. You have to look at this wave a little bit differently. The corresponding points are, let's say, one compression to the next compression. That distance would be called 1 lambda. That's kind of like one crest to one crest. Or you could consider that to be, if you picked another spot that was 30 seconds past the compression, then you'd have to pick that 30 seconds past the next compression as the corresponding place, and that could be considered the wavelength. But that's harder to see. So generally we think of it as compression to compression, or you could also go rarefaction to rarefaction. Those are the easiest ones to visualize. So that's how we get all these ideas. Amplitude, wavelength, and crests and troughs, compressions, rarefactions. And we have one more thing to talk about, and that is the mystery of the longitudinal wave. It looks different, but actually it's not. I want you to picture this. Picture a longitudinal wave on a graph. Whenever we graph things, it's like translating them into mathematics. So this is how mathematics would look at a longitudinal compression wave. Instead of graphing the position, let's graph the amount of compression on this y-axis as time goes on the x-axis. Well, look what's happening in our purple wave. We have a maximum amount of compression and then a minimum amount of compression, max and min. So that means that on my graph, I would start with a maximum amount of compression and a minimum amount of compression. As time goes by, I change from maximum to the minimum compression, and then I go back up and I get to the maximum compression, and then the minimum compression, and then the maximum compression. And voila! The graph looks exactly like the transverse wave. And in fact, it is exactly like the transverse wave. The amplitude is the amount of compression. Well, here is the amount of compression, because remember, I'm graphing compression on this side of the wave. So that becomes the amplitude. The wavelength is the distance between two compressions. Well, here's a maximum compression, here's a maximum compression, there is the lambda, the wavelength, the distance between two troughs or crests. I could do it here as well, between the troughs. So everything is exactly the same. So what this means is that although the two waves look vastly different, mathematically speaking, both types of waves are identical. Transverse and longitudinal waves are the same thing. So we have to get our head around the two types of waves and why they're a little bit different on the outside, why they appear to be different. But we can rest easy knowing that when we start describing waves, all we need is one set of mathematics. One set of equations, one set of numbers will describe all the types of waves that we need to worry about. So that means our life is incredibly simple. So, to summarize, what you need to do is you need to get your head around the vocabulary. And the best way to learn vocabulary is to not just read the words and know how to spell them or write a definition. Definitions are bad because we often use bigger words in the definition than we use for the word we were describing. What you need is a mental picture. When you see the word transverse wave, you need a mental picture in your mind, right? When you see the word compression wave or longitudinal wave, you need a mental picture in your mind. Amplitude, wavelength, crest, trough, compression, rarefaction, you need a mental picture. And the best way I find to develop mental pictures is either, well, in my day, it was draw pictures. Draw a picture beside each word that helps you visualize what it is. Or, in modern days, you can use the magic of Google Images. And if you go and Google images of amplitude or longitudinal or wavelength, you will get a myriad of pictures, millions of pictures, that will help you to visualize what it is you're looking at. And it will enhance your understanding of these concepts, because these are the beginning concepts that are critical to understanding how waves work, simple harmonic motion, how it translates into wave motion, and very soon we're going to apply this to two types of very important waves, sound waves and light waves. So we need to make sure we have all of this stuff, longitudinal. Don't forget about propagation direction and the direction of oscillation. Even the word oscillation might be new to you. So take your time, get used to this, learn all these terms, and then we'll start applying them to sound and to light. Sound, by the way, happens to be a longitudinal wave, and light happens to be a transverse wave. So they're good examples of each one. All right, and that's all for today.